All right, welcome to our next lecture. So today I wanted to discuss Newton's universal law of gravitation. Earlier in the semester we talked about this story, which is almost certainly fanciful, of Newton being struck by an apple in realizing gravity. Um, one uh, one thing I have heard uh, is that during times of plague, Newton would often retreat to his uncle's farm for the isolation, um, and uh, and he credited some of those times of isolation as some of his most productive. And what he did recognize is the same thing that causes the apple to fall is the same thing that keeps the moon in orbit. And so let's jump right into it. So Newton's universal law of gravitation can be written as follows. Um, F sub g of 1 on 2, so that's the subscripting that I use, the gravitational force of object 1 on object 2. So let's say that we have two objects, mass 1 and mass 2, separated by some center of mass separation distance r. Um, in this case, by Newton's third law, right, the forces they exert upon one another must be equal and opposite. And so this is uh, uh, F2 on 1, and this is F1 on 2. They are equal in magnitude but opposite in sense, opposite in direction. And we can describe them as minus capital G times m1 times m2 divided by r squared. And remember that forces are vectors, and the way that we're going to describe the vector is uh, with an r hat, where remember the hat is how I denote a unit vector. It has length 1. It just purely describes the direction, so it doesn't scale the vector. It only provides a direction. Capital G is 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. And um, I think that you'll probably use this enough times that it will roll off the tongue nicely. 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. Um, so there is that. The first thing I want to point out is, well, maybe the very first thing I'll point out is this minus sign just speaks to the attractive nature of the force. It means that it pulls. So the force that mass 2 exerts on mass 1, right? So our subscripting is force of 1 on 2. So let's jump to mass 2 for a second. The force that mass 1 exerts on mass 2 is described thusly. This minus sign just tells me that the direction of the force is such that that mass 2 is pulled towards mass 1, or at least tends to. The next thing I want to point out is this 1 over r squared dependence. This is actually going to become somewhat familiar to you as you move on to Physics 230 next semester. That the magnitude of the force actually falls off as the square of the distance. And so let's assume that these two masses m1 and m2 are placed such that they exert 1 Newton of force upon one another. If we double the distance between their centers of mass, we actually wind up reducing the force not by a factor of 2, but by a factor of 2 squared. So if it was 1 Newton before, if you double the distance, the gravitational force between them that one exerts on the other will be only 1/4 of a Newton. If you had tripled the distance between their centers of mass, and originally the force between them was 1 Newton. After you triple the distance, the force will be 1/9 of a Newton, which is 1/3 squared, right? If you triple the distance, the force drops by a factor of 3 squared, and so on and so forth. Closer to home, as it were, if you have a person standing on Earth, um, they exert the same force upon each other, right? Newton's third law, gravitationally. And the magnitude of such force is just the universal gravitational constant, capital G, 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared, times the mass of the Earth, which is about 5.98 times 10 to the 24 kilograms, times the mass of the individual, little m here, divided by the radius of the Earth squared. And remember, the Earth isn't actually a perfect sphere. Um, it's more oblate, and it deviates from that because it's uh, kind of lumpy. But the averaged radius is about 6,378,000 meters, give or take. Um, and so the gravitational force between them is such. But remember, previously we've said that the gravitational force goes as mg, and it's actually worked very well in our labs, right? And so if the object is placed on the floor, we have said previously that the floor needs to exert a normal force upwards to balance mg to keep this thing in equilibrium. And that gravitational force mg is apparently also equal to capital G MEM over RE squared. Note that there's a little m on both sides, and so we can cancel them. And that allows us to solve for little g. Little g is apparently the universal gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared, times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, and divided by the distance between the center of the Earth and the surface, which on average is about 6,378,000 meters. But remember, you have to square it. So if you do that, maybe pause the video and just try, see how close you get to the value of little g we've been working with all semester. The other thing I'd like to note is if you're at some height h above the ground, well, then the only way this really changes is that mg is still on the left side, but on the right side, instead of GMM over RE squared, you have GMEM over quantity R plus H and quantity squared. And so again, you can divide the little m across and divide it out such that you get that G is just equal, little g is equal to capital G ME over quantity RE plus H and quantity squared. Note that since the radius of the Earth on average is about 6,378,000 meters, unless h is pretty significant, little g doesn't change very rapidly, right? You're already dividing by a giant number. And so you're already dividing by the square of 6,378,000 meters. If you add a few meters onto that, if you add 10 meters onto that, and then square it, it really doesn't change your answer that much. It doesn't show up until far on down in the decimal place order. So where might you actually notice this? Well, the International Space Station actually orbits about 350 kilometers, 350,000 meters above the Earth's surface. And I would tell you that on Earth, it weighed approximately 4.22 times 10 to the 6 newtons, so 4.22 meganewtons. I'd like to know what's its weight in orbit right now. This is maybe not my best phrasing. What I really mean is what is the gravitational force acting upon it? Since it's effectively in free fall, it acts as though it's weightless. And so we should be a little careful with how we're writing this. But Note that when it was on the ground, we could say that m is just equal to Fg over g. So 4.22 times 10 to the 6 newtons divided by 9.8 meters per second squared. The International Space Station apparently has a mass of approximately 4.31 times 10 to the 5 kilograms. So then, let's figure out what little g is at the orbital height, right? This 350 kilometers above the surface of the Earth. And so we just say we just put this up here, right? Little g is going to be capital G times the mass of the Earth divided by the square of Re plus h. And so 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared times 5.98 times 10 to the 24 kilograms divided by 6.37 times 10 to the 6 meters plus 0.350 times 10 to the 6 meters quantity squared. Where is this 0.35 times 10 to the 6 meters coming from? Well, 350,000 meters, right? 350 kilometers is 350,000 meters. That's 0.350 million meters. Pardon. If you plug all that in, little g is apparently about 8.83 meters per second squared if you go 350,000 meters above the surface of the Earth. And remember, a basketball player is, it's not uncommon for a professional basketball player to be about 2 meters tall, maybe even a touch more than that. But the 350,000 meters is a lot of professional basketball players stacked upon each other, right? So if you go that high up, the acceleration due to gravity is still actually about 8.83 meters per second squared instead of the probably more familiar 9.8 meters per second squared that we're used to down here near the surface of the Earth. And so if we wanted to know what mg would be, the gravitational force acting upon the International Space Station while it's in orbit, well, we take its mass, we multiply that by little g, and if you do that, you take this mass and you multiply by this value of little g where it's actually at, you get about 3.8 times 10 to the 6 newtons, which, note, is not that different. It's about 90% of the gravitational force that acted on this thing when it was on the Earth's surface, right? So even that high up, so when something we say is weightless, we don't mean that there's no gravitational force. What we mean is that it's effectively in free fall. There's no normal force or other support force holding it up against gravity. Okay, let's use what we've learned to calculate Earth's density, or at least the average density. The Earth isn't uniform straight through, right? And so this allows us to calculate the average density. But what we would say is that density in general is mass over volume, right? So in this case, the density of the Earth is the mass of the Earth divided by the volume of the Earth. We also have just gotten through saying that at the surface of the Earth, little g is equal to gme over re squared. We could solve that for the mass of the Earth. It's just little g times re squared over capital G, right? So if you go from here to here, that's just algebraic manipulation. So we could plug that in for ME, right? We just solved for ME, so we plug that in for ME. And the volume of the Earth, well, I know I keep telling you it's not a perfect sphere, but let's approximate it as pretty close to a perfect sphere. And the volume of a perfect sphere is just 4/3 pi r cubed. And so if we take the mass of the Earth, which is apparently g re squared over capital G, and divide it by the volume of the Earth, which is apparently close to 4/3 pi r cubed, and then just, again, algebraic manipulation yields 3/4 little g divided by pi capital G re. And so plug in some of the stuff we know. Little g at the surface of the Earth is about 9.8 meters per second squared. Capital G is 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared. The radius of the Earth is approximately 6.37 times 10 to the 6 meters. And so if you plug all that in into your calculator, you'll get that the average density of the Earth is about 5,510 kilograms per cubic meter. If I were to tell you that the crust of the Earth is only a couple thousand kilograms per cubic meter of density, like if you just go outside and dig, or if you were to look at the density of granite is about 2,750 kilograms per cubic meter. What does that imply? Well, if the average density is more than the density here near the surface, like near the crust, well, in order for the average to be greater than the value at the crust, the stuff inside must have a greater density. And so from this, you would probably expect that from those two pieces of information that the average density is about 5,510 kilograms per cubic meter, and that the density near the surface is a couple thousand kilograms per cubic meter. You would expect that the interior regions of the Earth are more dense. Hopefully that makes sense. All right, so let's add Kepler's laws to the mix. I think that this is kind of cool. So this isn't really a required piece of the class, but it's neat enough that I want you guys to see it. So it's a good way of doing examples with gravity. And some of the other topics we've covered over the course of the semester. So Kepler's first law is that all planetary orbits are ellipses with the sun at one focus. And so we could put the sun right here, right? Just for completeness sake, note that I borrowed this image from Wikipedia. So there is the attribution, but this is an elliptical path, right? And so if this is the sun, this is one of the sun sits at one of the foci, the planet would orbit on this path. I would tell you that in our solar system, most planetary orbits are much more circular than this. So remember, a circle is just a special ellipse. So ellipses have two foci. A circle is just an ellipse where both foci sit at one point, right? So basically, as you bring the second focus point towards the first focus point, this thing becomes circular. That's what I mean by that. And in our solar system, the planetary orbits are elliptical, but they're much close. They have a high level of, if you squint, they look like circles for the most part. Now comets often have very elliptical orbits, and so that's that is comets and asteroids are also bound to follow Kepler's laws, just as planets. Kepler's second law. If you draw a radius vector connecting the sun to the planet, and you follow that radius vector over time, it will sweep out an equal area in equal time intervals. So if the planet was here, and then 1 month later it was here, when it's far away from the sun, then when it's close to the sun, if it's here, 1 month later it will be here, such that the area swept out by the line connecting the sun to the planet, A1 when it's over here, A2 over here, those two areas, if it took 1 month to travel in both of those cases, A1 must equal A2. That's what's meant by this statement. You could think of this, you know, why physicists don't get invited to pizza parties. At least build your own pizza parties. Pizza comes out of the oven. It's not a perfect circle. It's maybe elliptical. The you know the physicist might cut a slice like this, right? Like A1. You want to make sure that all of your guests get equal areas of pizza, and so the next slice has to uh, be much wider but much shorter, right? Does that make sense? So these two areas are the same. This one is long but skinny. This one is shorter but wider. Hopefully that makes sense. We can justify why this is true. Torque is equal to R cross F. And so in this case, torque, the force that causes the planet to orbit, is gravity. So that would be R cross F sub g. But remember, the gravitational force is itself directed along this radial axis. And so R is going to be parallel to this gravitational force, which is along R hat. And so since the cross product multiplies perpendicular components, there are no perpendicular components, and so the torque here is going to be 0. Well, you probably remember that that a force exerted over time is going to change the linear momentum, right? That's our impulse. A torque, instead of a force, a torque exerted over time is going to change our angular momentum. And so what that tells us is that the angular momentum, r cross p, is going to be constant. And we could rewrite r cross p as m, the mass of the planet, times r cross v. In order for the angular momentum to be constant, that means that the mass of the planet times r cross v has to be constant. So when r is big, when the planet is far away, that means v has to be small. So it's not traveling very fast. That's why it only goes from here to here in a month. But when it's near the sun, r is now short, r is small. In order for r times v to still be a constant, if r gets small, v has to get big, and that's why in the same 1 month period, it would travel a much greater arc length when it's near the sun versus far from the sun. Hopefully that's all right. In fact, we can go further than this. We could, here is my r vector connecting the sun to the planet. Then this incremental bit of area, dA, is just going to be half times r times dr. And it's actually r cross dr. But we could say that dr is just going to be v dt, right? V is dr dt, so dr is just v dt. Y half, well, r cross dr is going to make a parallelogram. We're not getting the whole parallelogram. We're only getting one. We're only getting 1/2 of it, the part on one side of the diagonal. So then I'll pause this for a moment. So I've drawn the other bit of the parallelogram, right? So if you take r cross dr, it's going to sweep out it's going to create this parallelogram, but we're not getting all of that. We're only getting the part that is bound by the diagonal r. And so cut that in half. That's why dA is half r cross dr. So I don't want the incremental area vector, I just want the magnitude. I just care about how much area. And so I'm going to take the absolute value of r cross v dt. And since we said that L is going to go as m r cross v, well, we have an r cross v here, that's equal to an L, if we also had an m, right? And so if I multiply top and bottom by m here, then I get L over m planet, and then I need to account for this half, and so that's where the 2 came from. And then I also have this dt just floating out there, right? And so what we get is that dA is equal to L times 2m, L divided by 2m planet times dt. I could divide both sides by dt, right? And if I do that, we get that dA dt is just L over 2m planet, but we already said that L was a constant. And so the mass of the planet presumably is somewhat constant, assuming it's not getting bombarded by stuff too often. Then dA dt is just equal to L over 2m planet, but L's a constant, m planet's a constant, and so all of this is a constant. What this says is that dA dt is a constant. In other words, the rate of change of area is a constant, which is consistent with this picture, right? That in the same amount of time, you get the same amount of area. That's Kepler's second law. Kepler's third law is that if you take the square of the orbital period, so remember, it takes 1 year for Earth to orbit Sun. If you take the square of the orbital period for any planet orbiting our Sun, it's going to be proportional to the cube of the semi-major axis of its elliptical orbit. So for the Earth, we are approximately 1 astronomical unit away. Just by definition, the average distance between us and the Sun over the course of the year is 1 AU, 1 astronomical unit. And it takes 1 year for Earth to orbit Sun. And so if we square the orbital period, 1 year squared is 1 squared, right? It's proportional to the cube of the semi-major axis of the elliptical orbit. Well, we're about 1 AU away, so 1 squared is also equal to 1 cubed. So if you pick the right set of units, if you use Earth years and astronomical units, then you can actually say that the orbital period squared is actually equal to the semi-major axis cubed. If it's measured, the period is measured in Earth years, and the semi-major axis is measured in astronomical units. But let's see where this comes from. And here again, note that I've kind of drawn circular orbits just for simplicity's sake, and I'll broaden this at the end without justification. But we could apply Newton's second law, right? The sum of the forces is equal to ma. Well, in this case, the force is gravity, and so capital G times the mass of the Sun times the mass of the planet divided by the orbital distance squared has to equal ma, well, the mass of the planet times the centripetal acceleration v squared over r. We have this equation. This is just Newton's second law, right? And we can say that the average speed here is just the circumference 2 pi r divided by the orbital period t. So v is just going to be 2 pi r over t. And this is fair for the circular orbit. Note that there's an MP on both sides of the equation, so I can divide through, cancel. And what we're left with on the left is g times the mass of the sun, capital G times the mass of the sun, divided by the orbital distance squared, is equal to v squared over r, but we just said that v was 2 pi r over t. So on the right side, we have quantity 2 pi r over t and quantity squared in the numerator divided by r in the denominator. You can perform the algebra as well as I can, and what you'll find is that capital T squared, the period squared, is going to equal 4 pi squared over capital G times the mass of the sun, all of that multiplied by r cubed. But note that 4 pi squared over gm is all constant, right? And so I could replace this with just some constant. In fact, we often do. This Kepler constant is 4 pi squared over gm sun, and it's equivalent to about 2.97 times 10 to the minus 19 seconds squared over meters cubed. So if you don't use Earth years for period and astronomical units for semi-major axis distance, if instead you decide to use seconds for period and meters for distance, then it's not that t squared is equal to a cubed. It's that t squared is equal to k times a cubed, where k is 2.97 times 10 to the minus 19 seconds squared over meters cubed. We can make this more general by saying that t squared is 4 pi squared over gms times a cubed. So here, note that I said r because I was treating the orbit as perfectly circular. As it turns out, it's a little bit more complicated mathematically, and so I'm going to skip it. But if you just take the semi-major axis, right? So the semi-major axis A is just the distance from the midpoint to the long edge of the ellipse. You can replace r directly with the semi-major axis A. So that's Kepler's third law. So if we wanted to know the mass of the sun, we can actually figure this out. There are about 31 million seconds in a year. I'm sure my lectures feel like they're themselves 31 million seconds sometimes, but believe it or not, my lectures are a small fraction of your year. But you get that by taking 1 year times 365 and 1/4 days per year, multiplied by 24 hours per day, multiplied by 60 minutes per hour, multiplied by 60 seconds per minute. If you multiply all that stuff together, you'll find that 1 year is equivalent to 31 million and change seconds. And the average distance between us and the sun is again 1 astronomical unit, which is about 1.496 times 10 to the 11 meters. I normally don't use that many decimals. I normally just say it's about 1.5 times 10 to the 11 meters. And I think we've actually done that in lecture before. It's a lot easier to just remember that round number. So if you plug in, so first you could come back to this equation, solve for mass of the sun. You get 4 pi squared r cubed or a cubed over gt squared, plugging in what we mean for r and what we mean for the period t. Period t is 31 million seconds, give or take. If you plug that in, you get a mass of the sun of about 1.99 times 10 to the 30 kilograms. Remember, the mass of the Earth is about 5.98 times 10 to the 24 kilograms, so the mass of the sun is substantially larger, as you probably expected. For a satellite, we could kind of adjust what we did up here. So a satellite isn't orbiting the sun directly, it's orbiting the Earth, right? Um, so we could write this where instead of using mass of the sun, we could use mass of the Earth, and instead of mass of the planet, we could use mass of the satellite, and instead of mass of the planet here, mass of the satellite. If we do that, we have this equation, g times the mass of the Earth times the mass of the satellite divided by r squared needs to equal the mass of the satellite times v squared over r. It's again just Newton's second law. It's right here. Yay? We could solve this for v, and somehow I have switched again from this v to this v, but forgive me. V is equal to the square root of gme over r, but remember this r is the distance from the center of the Earth to the center of mass of the satellite. And so really we could write this as little r is equal to the radius of the Earth plus the height above the surface h. Yay? Let's assume we want geosynchronous. A geosynchronous satellite is the type of satellite that is often used for communications and telecommunications when satellites are involved, because they always appear to be at the same point in the sky. That way you can just kind of aim your satellite dish at the satellite and not have to mechanically adjust the satellite dish all the time to have it still pointed at the satellite. So in this case, we have this statement, and again, we're going to replace the mass of the sun for mass of the Earth. So we have t squared is equal to 4 pi squared over gm Earth times r cubed. Solve this for r, and we get that the radius is g times the mass of the Earth times t squared over 4 pi squared, all of that raised to the 1/3. We're going to plug in so in order for the satellite to always appear at the same point in the sky, it has to complete one lap in the same amount of time it takes for Earth to spin around on its axis once. And so it has to complete one lap in 24 hours so that it is kind of just keeping pace with the Earth as the Earth spins, or with a point on the Earth's surface as the Earth spins. And so here we need to figure out how many seconds are in 24 hours. So again, 24 hours times 60 minutes per hour times 60 seconds per minute is about 86,400 seconds. And so if you plug in that for t, 86,400 seconds in for t, you get a radius from the center of the Earth to the center mass of the satellite of about 4.23 times 10 to the 7 meters. If we want to figure out what the speed of a geosynchronous satellite is, then we can come back to this equation that we just solved for and plug in this for r, right? And so gme over r under the square root, where g is 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. Me, the mass of the Earth, is 5.98 times 10 to the 24 kilograms. And r, we're going to plug in 4.23 times 10 to the 7 meters. If you do that, you see that the speed of the geosynchronous satellite needs to be about 3,070 meters per second. Hopefully that's okay. I'd like to talk about fields, because there's a couple of things that Newton was distressed about in Newton's law of universal gravitation. So we come all the way back here, right? There are a couple of things that Newton found disturbing. One is he was basically forced to figure out how the moon orbits. He was basically, or how that relates to the apple falling. He was basically forced to calculate this as though all of the mass of the Earth were located at its center of mass. And it's actually one of the things that drove his calculus. Um, so Newton spent a few years developing calculus, and one of the first things he checked is, could he justify this idea that uh, that this object gravitationally acts as though all of its mass is at its center of mass, and lo and behold, calculus bears this out. Um, Another thing that distressed him is this idea of action at a distance. Um, Physicists are sometimes a little troubled by that sort of thing, right? Action at a distance, that the Earth can affect the moon and the moon can affect the Earth without touching at a distance. Um, that's a little disturbing. And so one of the ways that Newton approached this is he introduced this idea of a gravitational field. The uh, the Earth has a gravitational field, and so does the moon. Um, it's not that the in this model, and this is a model, it's not that the uh, Earth is influencing the moon from a distance. Instead, the Earth generates an, uh, a gravitational field that permeates all of space, and the moon is just interacting with the Earth's gravitational field at the point at which uh, the, the moon happens to be. And I've tried to draw this, and I think I've drawn this as about as poorly as you can. Um, but I've tried to use arrows of varying length. As you get further away, remember that the gravitational force drops off as 1 over r squared. We're going to define the gravitational field, little g, to just be the gravitational force over some test mass. And if you do that, you get minus g, at least for the Earth, minus g me over r squared r hat. If you wanted to find the gravitational field of something else, instead of the mass of the Earth, you would use the mass of whatever that something else is. But notice that the gravitational field is also going to diminish in strength as 1 over r squared. And so as you go further away, these arrows are meant to get smaller and smaller and smaller. Why haven't we noticed that in lab? Well, again, because at the surface of the Earth, you're already 6,378,000 meters from the center of the Earth. You have to go pretty far before you start to see a big deviation in the Earth's gravitational field. Um, it's locally about 9.8 meters per second squared towards the center of the Earth. I've kind of taken this tiny little swath of Earth and blown it up over here for you. And so in our lab, um, we are looking at such a tiny, tiny little section of the Earth. It really does seem as though the gravitational field points straight down, and uh, and is fairly uniform, right? Because we're not, our lab isn't tall enough to notice any substantive difference in the value of in magnitude of little g, and the direction of little g. Our lab isn't wide enough to notice any substantive difference in the direction of little g. Our lab would have to be uh, wide enough to actually account for this curvature of the Earth for us to be able to not have all of these field lines pointing uh, straight down in parallel to one another. Let's talk about gravitational potential energy. Um, and so here we have a particle that is originally at A, which is some distance r sub e, r earlier. I'm realizing that RE here probably makes you think of radius of the Earth. I don't mean that. I mean here earlier. Maybe I should have used initial and final. But point A is some radial distance RE away from this origin, and we're going to head to some point B, which is some radius RL away from the origin. And we're going to subject this to radial forces, like Earth's gravity. And so the first thing I'll remind you of, oh, and maybe I should, uh, uh, so the path that I'm going to take an arced path. So these are all radial lines, right? All these dashed lines are radial. And all of these forces are meant to be radial, even though I don't have steady enough hands to draw them as straight lines. We're going to take some arced path from this first dashed line to the second dashed line. And if we do that, remember that this radial force is going to be perpendicular to this gray path everywhere, right? And then I'm going to follow this radial line up here to get, I'm trying to model kind of this green path with a bunch of tiny little steps. And so an arc, and then a radial step, and then another arc, and then a radial step, and then another arc, and a radial step, another arc, a radial step, another arc, a radial step, another arc, a radial step, and finally one last arc. The thing that I want to point to is that earlier in the semester we said that the incremental bit of work done is just equal to the dot product, the scalar product of force and dr. And so in this case, since the force is purely radial, F dot dr, the dot product just multiplies parallel components. F dot dr is going to equal F times dr for each of the radial steps. Each of the pieces that follows these dashed lines, the incremental bit of work done is just going to be F times dr. But for the arc steps, because the force is radial and the arc is tangential, they're perpendicular to one another, there is no parallel component to multiply, and so F dot dr for the arc steps is always 0. And so we can get the total work done just by integrating the tiny little incremental bits of dw. Well, all of these are zeros, so all of the arc steps contribute no work. But the radial steps each contribute FDR. And so we're just going to integrate from the earlier radius to the later radius of FDR. In other words, the work only depends on this radial force. And so since the work is going to change the energy state of the system, we can say that the change in potential energy is going to go as u later minus u earlier. It's just going to be minus this integral. So the change in potential energy is just going to be minus the integral from the earlier radius to the later radius of f of r times dr. Here, because we're talking about gravity, f of r is going to be minus universal gravitational constant, capital G, mass of the Earth times the mass of whatever this object moving from A to B is, divided by r squared. And so plugging that in, delta U, so if you plug in this in for F, you'll get that the change in potential energy, minus sign cancels, is GMEM times the integral from RE to RL, earlier radius to later radius, of dr over r squared. This is actually not a terrible integral, right? It's just equal to minus 1 over r, and the limits are going to be from the earlier radius to the later radius, and we still have to multiply by the prefactor GME times m. Now, if you plug in RL and RE in for R, you get the change in potential energy is just going to be the universal gravitational constant G, 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared, times the mass of the Earth, 5.98 times 10 to the 24 kilograms, times the mass of, again, whatever particle we're carrying from point A to point B, times the quantity of 1 over the earlier radius minus 1 over the later radius end quantity. We could do the same fancy trick we used earlier in the semester and set the 0 point of potential energy wherever we want. And we could just say that the function describing the gravitational potential energy as a function of radius is just minus g, where minus the universal gravitational constant g times the mass of the Earth times the mass of the particle divided by r. And so in this case, or if we want to do this more generally, it doesn't just have to be for Earth. It could be for any pair of particles. We could look at the gravitational potential energy in any system of a pair of particles, center of mass separated by r. It's just going to be minus universal gravitational constant 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared times m1 times m2 over r. So if we wanted to, we could come all the way back up to here and figure out the gravitational potential energy of this system of two masses m1 and m2 separated by some center of mass separation distance r. And we get that the gravitational potential energy of that system is just minus capital G times m1 times m2 over r. All right, let's calculate escape speed. Again, because this is cool. So if you're standing on the surface of the Earth and you throw a baseball straight up, well, we could just conserve energy, right? You threw this thing upwards with some speed v earlier, so it has kinetic energy when it leaves your hand of half mv squared. It has gravitational potential energy of universal gravitational constant g times the mass of the Earth times the mass of the ball divided by the radius of the Earth, right? We just solved for that here, right? That is the potential energy. I guess it was this one, right? Yay. So then this is the energy as it leaves your hand, right? Kinetic energy and potential energy. When it gets to its maximum height, it will not have any speed anymore, right? It will, just like throwing a pencil up at its maximum height, it has no speed instantaneously, at least. So at that point, it should only have potential energy. And so we could say that at that point, the total energy is just minus g mass of the Earth times m, the mass of the ball or whatever it is you're throwing, divided by the value of r at its maximum height. Well, this we can solve. We could solve this for v earlier, right? This is just an algebra problem at this point, so you can manipulate this equation, and if you do, it will solve to something like this. V earlier squared is equal to 2 times the universal gravitational constant g times the mass of the Earth times 1 over the radius of the Earth minus 1 over the radius at its maximum height. We could also remember that that the maximum height h is just going to be the radius at its maximum height minus the radius of the Earth, right? That is in picture form here. H is just equal to r at its maximum height minus the radius of the Earth. Yay? So in that case, let's calculate the escape speed. Well, in order to escape, I want this thing, if I throw the pencil up, it gets to its maximum height, then it falls back down, right? I want to throw this thing so far away that it doesn't come back. And so I want to let the maximum radius, or the radius at its maximum height, approach infinity. And so if I do that, I plug in infinity for this. 1 over infinity is 0, right? And we get that VE squared, V earlier squared, is just 2G, 2 times the universal gravitational constant G times the mass of the Earth times quantity 1 over the radius of the Earth minus 0 and quantity. We could square root both sides, and we get that the escape speed is the square root of 2 times G, the universal gravitational constant G, times the mass of the Earth divided by the radius of the Earth. You could plug in values, and if you do, you'll see that the escape speed from Earth is about 11,200 meters per second. Now, this is if the speed it has to have when it leaves your hand, not the speed it would need if you were going to keep pushing, right? If you have a rocket booster on this, that's a different story. This is just assuming you throw it, and from then on, it's only affected by gravity. A physicist named Schwarzschild actually used this to calculate the size of a black hole. And so what he did is he set the escape speed equal to c, the speed of light, which is about 3 times 10 to the 8 meters per second. And he solved for a given mass, so pick whatever mass you want. He solved for the radius, and that radius is what we call the event horizon. It turns out for a class of non-rotating black hole, this actually gives the right answer. The Schwarzschild radius, you now have the ability to solve for the radius of a non-rotating Schwarzschild black hole. Just by solving this equation for r, setting the escape speed equal to c, the speed of light, 3 times 10 to the 8 meters per second. And then as you vary the mass, the radius will change, right? As it turns out, the derivation that he used wasn't entirely correct. There are 2 bits of 20th century physics that you'll learn if you take Physics 231 or 3rd semester with us. One of them effectively makes his answer 2 times too big. The other makes his answer 2 times small. If you multiply by 2 but then divide by 2, you get the same answer. So he gets the right answer. It's just a slightly oversimplified way of getting there. But it's still cool. You now know enough physics to determine the radius of a black hole of a given mass, just by solving this formula. So, all right, I am out of time. I was trying to keep this to under an hour, and I have just barely done so. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow.